So having discussed the perception and localization and what the functionalities of perception and localization algorithms are in a robot, we can now understand the area of planning. So set of all algorithms that plan the trajectory as well as the behavior of the vehicle on road or in an environment, we call them planning algorithms. Sometimes we call them, in the context of autonomous driving, we call this motion planning and decision making. So typically the planning problem for an autonomous driving for a robot is broken into 3 or 4 different pipelines. So these are pipelines or components. So these components are route planning, or sometimes we call it mission planning. The next is trajectory or motion planning. Motion planning, trajectory planning, and also path planning. The third component is the behavior planning or the decision making algorithms. Behavior planning or decision making algorithms. Once we have planned, so the decision makers and the motion planner or trajectory planner combinedly produce a local trajectory and a set of behaviors along the trajectory for a robot or a vehicle to execute. And these behaviors and this trajectory is executed by a set of control algorithms. For example, in the context of autonomous driving, no matter what behavior plan or what trajectory plan you come up with, ultimately you will have to convert that plan into following. You have to sort of break it into the accelerator command. Perhaps if you are having a manual transmission vehicle, then you have to also have a command for the clutch. Most importantly, you will have a command for brake and accelerator. And steering wheel. Similarly, let's suppose you are having an industrial or warehouse robot, where the robot, instead of being an Ackermann dynamics vehicle, so the vehicles that have a steering wheel, they follow the Ackermann dynamics principle. Now let's assume that you have a differential drive robot, perhaps a 2-wheeled or 4-wheeled differential drive robot. So in differential drive robot, perhaps you would generate a command for the speed or the velocity of the left wheels and the right wheels. So by generating different velocity commands for the left wheel and the right wheels, the robot can turn, move, and go at a certain speed. So based on a robotic system, we will have a different sort of control algorithms. So these control algorithms take the high dimensional plan as an input, and they break it down into the low level control or motor commands in a robot or an autonomous driving vehicle. To give you a brief high-level idea as to what planning in an autonomous driving vehicle would look like, let's consider this image as an example. So again, this image is captured using the cameras mounted on our autonomous driving vehicle. And as you can see, like we have had an algorithm that detects where the road is. So having understood the perception and localization algorithms, we know that the perception algorithms compute all the necessary information for an autonomous driving vehicle for it to build a 3D or a projected 2D representation of the world around it. Similarly, we have seen that localization algorithms localize a vehicle on road so that it knows where it is on planet Earth. And depending, for example, most of the autonomous driving vehicles in the autonomous driving companies in the world, they are building the technology that is highly dependent on the global accurate positioning of the vehicle on road. So for them to function properly, they would perhaps require a 10 to 15 centimeter error in localization, whereas the technology that we are working on at Swiat Robots, we are not too centric on the global accurate positioning of the vehicle. But for the sake of the discussion, we don't go into the details as to what is important, what is not important for autonomous driving vehicle. Let's consider this autonomous driving in general. Now let's assume that we have again localization algorithms that can localize a vehicle with perhaps 10 to 20 centimeter localization error. And let's assume that we started from point A and our goal is to reach a point B. So the route and mission planning problems, so let's suppose we have a road network that looks something like this. And let's suppose our goal is to reach this point B and we started somewhere from point A. So a route planning algorithm or a mission planning algorithm will plan a global route for the vehicle to follow. And this route planning, whether the mission or the route plan takes this approach or this approach, it depends on various factors. For example, we can take the traffic into account, we can take the road terrain into account, we can take the, for example, we can have a cost function that heavily penalizes the length of the trajectory or the distance the vehicle has to cover. So in that case, the mission or the route planner will select the path that is of minimum length. Likewise, we can penalize the time required to reach the destination. In that case, the route planner or the mission planner will take the traffic scenario into account. It can take several other factors into account. It can take the terrain map into account. Because the terrain is rough, then the vehicle would navigate at slow speed. If the terrain is smooth, then the vehicle can navigate at very high speeds. So taking the various factors into account, the route or the mission planner will come up with a global plan for the vehicle to follow. Let's suppose it selects this route. So once the vehicle knows where to go, then it's all up to the perception and the planning algorithms for to take the vehicle safely to its destination. Localization, again, I mean, some companies depend heavily on global accurate positioning, but we on the other hand at Swiat are developing a cutting edge technology that doesn't require global accurate positioning of the vehicle on road. It just uses local relative localization for keeping the vehicle safe on road. But keeping that discussion aside, let's assume we also have a localization algorithms that can localize a vehicle on road with 10 to 20 centimeter error in localization. So in that case, let's assume that the vehicle is navigating on this road, right? So what are all the algorithms that this vehicle would need to actually execute all its maneuvers safely to reach the destination? Perhaps the very first algorithm we would need is a route planner. So the route planner has given us a global trajectory for the vehicle or robot to follow. So assuming that the route planner or a mission planner has already provided us a road network to follow, where we know all the turns and exits to take to reach our destination, and assuming that we have the perception algorithms that can detect all the necessary information, for example, road, perhaps lane markers and road boundaries. Perhaps we have algorithms to build a terrain map, assuming that we also have algorithms that can compute the velocities of the obstacles on road, and any necessary algorithm that we need to actually perceive the environment, assuming that we have all such algorithms, and assuming that we also have localization algorithms that can position the vehicle accurately globally with 10 to 20 centimeter precision on road. So so consider this image as an example. Let's suppose our vehicle is navigating on this road. So what are all the algorithms, what are all the planning algorithms that would be needing to keep the vehicle safe on this road, as well as enable the vehicle to reach its destination? So perhaps the very first algorithm we'd be needing is a local trajectory planner or a motion planner or a path planner that plans the trajectory of the vehicle. Let's suppose it looks something like this. Then we can see that since this is a generalized autonomous driving vehicle, and assume when you are driving a vehicle on road, what are all the decisions that you make when you're driving a vehicle? You make decisions like what speed to drive at. You make decisions about overtaking other vehicles. If you're already in the midst of overtaking, and as you know in India, I mean on typical 2-lane roads, when there's a traffic coming from the other direction, you sometimes make a decision to abort your overtaking. If you feel that this overtaking is not going to be successful, then you abort. So perhaps you may need a decision maker for that. I mean, again, if you're driving in India, you know that sometimes you have to yield away to a truck or other vehicle coming from the other direction. So we need to have a decision maker that decides when to yield, how much to yield, at what speed to yield, right? Because it's a multi-agent game that we're playing on road, right? So we'd be needing perhaps all such algorithms to actually keep the vehicle safe on road. So perhaps you would be needing, for example, to conserve, for example, the problem of overtaking. Let's suppose, as we can see, our vehicle is currently in the midst of overtaking. So we are overtaking these trucks, and we can see that there is a car and a bike that is coming from the other direction. So perhaps we need a decision maker that takes the velocities into account, that takes the dynamics of the ego vehicle into account, it takes the dynamics of the other obstacles into account, and taking all the factors as to what actions we can execute and what actions other obstacles or other vehicles in the environment can execute. Let's suppose this algorithm has a capability to evaluate, to take all this information and compute the probability of a vehicle being safe, and based on that probability it decides whether to keep on this overtaking or to abort the overtaking, right? Similarly, we would have an algorithm that initiated this overtaking. Likewise, we would have an algorithm that perhaps decides whether the overtaking first should end with this truck, or they should keep on continuing with two trucks in a continuous fashion, right? So you can see, I mean, the number of planning algorithms, or the kind of planning algorithms that we're needing to keep the vehicle safe on road, it again depends on application. For example, if you're driving in an industrial setting, right? Let's suppose you have a robot that is driving in an industrial setting, and let's assume that they are very narrow roads. So assume this is a forklift. This is an automated forklift. And it's driving in this industrial corridor. And these are, some of the blind spots. So these are blind spots. And assume that this forklift is navigating at perhaps maybe 5 meters per second and is carrying a load of 1000 kgs. So in case of an autonomous driving vehicle, let's suppose if we have the traffic coming from the other direction and the decision maker decides to slow down. So perhaps we would have a decision maker that decides whether to slow down or not. So motion planner, the algorithms that plan trajectory, they can inherently compute all these, the speed that the vehicle should be navigating at based on the speed of the other obstacles and the vehicles on road. But additionally, we have too many decision makers as well in an autonomous driving vehicle, and they work in parallel to to, to keep the vehicle safe on road. So if we are talking about a generalized autonomous driving, then there's a lot of information sharing that happens between a trajectory planner and a decision maker. So there are too many decision makers. For example, in SWAT's autonomous driving vehicle, in typical experiments that we do on tight roads, there are roughly 15 decision makers, and there are roughly 3 different motion planners that plan the motion of the vehicle on the road, coming up with a time parameterized trajectory, whose task is to keep the vehicle on safe. Additionally, we have decision makers that are also trying to keep the vehicle on safe. So they work in parallel, and there's a lot of information sharing. And typically, the behavior planner appends the decision on the trajectory that is computed by a motion planner. And this is how an autonomous driving vehicle works. It's a very complicated, discussion, but we will just restrict our discussion to give you a very high level idea as to what planning algorithms do. We'll just restrict our discussion to this industrial robotic scenario. So assume that we have a robot that is navigating, or automated forklift navigating this corridor, carrying 1000 kg weight at 5 meters per second. So an autonomous driving vehicle, if it needs to slow down, it can apply the brakes. For example, if we are feeling that there's going to be an imminent collision, we can apply hard brakes. At the same time, we can apply the steering command as well to actually steer away from that collision if the vehicle is not already in what we call inevitable collision states. We would be discussing all these concepts later on in module 4 as to what typical path planning and motion planning algorithms there are, what the dynamics of a robotic system, and what is an ICS, inevitable collision state. So we'll be discussing all these concepts in the module 4 of this course. So we don't care as to what these algorithms or what these terms mean at the moment. We are just discussing the field at large. So in case of this forklift, an autonomous driving vehicle can apply hard brakes, but if we apply hard brakes, in this forklift at 5 meters per second at 1000 kg load, then there's a chance that this entire forklift may just topple, right? And we would have a huge disaster, right? So we would be needing algorithms that take the uncertainties or the unforeseeable situations. For example, if a person suddenly comes in front of this forklift from this blind spot, then this vehicle, this forklift, should have planning algorithms that take this uncertainty of a person coming from these blind spots into account and select a velocity profile and a trajectory at every given time step, that even if such a situation happens, the vehicle shouldn't be in a situation that it needs to apply the hard brakes, which may result in toppling of this forklift, resulting in a huge damage, right? So in autonomous driving, perhaps, although autonomous driving is a much more complicated problem, but still, I mean, we can apply hard brakes over here. Just for example, in some cases we can apply hard brakes, but in an industrial setting with a 1000 kg load carrying forklift, this may not be a good scenario, I mean, to apply the brakes. So you see, the kind of behavior planner or the trajectory planner, the motion plans that we're needing for this industrial robot significantly differ from the kind of algorithms that we'd be needing for an autonomous driving vehicle. Furthermore, the localization of the robot in an industrial setting plays a very important role. For example, you are carrying a load, and the task is to place this load at a particular configuration, at a particular angle, and a very specific position, and a very particular orientation. So to execute this task of placing this load at a very specific position with a very specific orientation where the margin of error is very small, localizing this forklift relative to the environment is very important. So perhaps in this case we would be needing a localization error of 5 centimeter or sometimes even less than 5 centimeter, perhaps 2 centimeter localization error, right? So depending on the application, we have different kinds of planning algorithms. But one thing is sure, that we would always be needing a route planner. We would be needing trajectory or motion planner. So we would be using the term trajectory planner, path planner or motion planner interchangeably, although path planning slightly differs from the motion planning. And trajectory planning can be considered as a subset of the generalized motion planning, but we would just use these terms interchangeably, and we would clear the differences between them whenever it is required, for example mostly in module 4 of this course. And the other component that we need is a set of decision makers. So the decision makers take the future uncertainties into account, and they have a lot of control over the velocity profile along the trajectory that typically a trajectory planner or a motion planner plans. So typically motion planner and trajectory planner output the velocity profile as well, but usually in robotics or in autonomous driving we don't follow directly the velocities computed by a motion planner, even when we are doing what we call time optimal motion planning. In the time optimal motion planning, the motion planner would be outputting a trajectory that has x, y and perhaps z component, and it would have vx, the x velocity, the vy and vz velocity components that the robot should follow at each of the points on the trajectory. But typically it may be very hard to follow, because typically the dynamics of the vehicles are too complex and we do not take the full dynamics into account while planning the trajectory, and that is why we have a set of decision makers that control this velocity profile, that alter this velocity profile so that the vehicle can remain safe in an environment, taking all the future uncertainties into account, right? For example, these agents may change their speed, and a motion planner may have a hard time in keeping the vehicle safe without having very specific decision making algorithms. And typically, I mean, there is no end to the mathematics that you can read to make yourself a very good researcher or a very good engineer in planning algorithms. But typically in motion planning, we use any field of mathematics imaginable to come up with a novel motion planning algorithms. In decision making also, there is no end to the mathematics that we can study to come up with very robust decision makers. But typically, I mean, to give you at a broad idea, for example, if you're starting the field of decision making, perhaps you can read machine learning. You can study reinforcement learning. Sorry. We can study game theory. We can also study mathematical or generalized like topological theory. We are using this theory heavily in motion planning at Swift robots. And perhaps any kind of, for example, we can study probabilistic graphical models. And similarly, we can study any different branch of applied mathematics as well to come up with the novel or very robust decision making and motion planning algorithms. To summarize, planning algorithms have following components: a route planner or a mission planner, a motion planner, or we can call it motion planner, trajectory planner, or path planner, although trajectory planning and path planning is a subset of generalized motion planning. We also have a set of decision makers that plan the behavior of the vehicle on road. And then finally, we have control algorithms that take the high level plan planned by decision maker and motion planner, and they convert that plan into the local control commands for a robotic system or an autonomous driving vehicle.